Right now, while you are watching this, there is a hole in the sun. Not a hole you could fall into. A hole in the sun's outer shell, where its magnetic field just stopped doing its job. Through that gap, a river of charged particles is rushing out into space at almost double its normal speed, and it is aimed straight at Earth. Space agencies around the world are calling this the sun's most dangerous stretch of days and weeks, and the timing could not be worse. The sun is also sitting in the most violent phase of its 11-year cycle, and just days ago, one sunspot looked like it was about to become the strongest flare machine on the entire surface of the star. Then something strange happened. It was not the region everyone expected to blow up. Stick with me, because by the end of this video you will know exactly which part of the sun to actually watch, what could happen if this week tips the wrong way, and why a storm like this once made people read newspapers by the glow in the night sky alone. Section 1. A hole pointed straight at us. Let's start with what is happening tonight, because it is already in motion. The Space Weather Prediction Center, the government agency that tracks solar storms the same way weather stations track hurricanes, has a watch out right now. It says a geomagnetic storm is likely tonight into tomorrow, July the 22nd. The cause is not an explosion on the sun. It is something quieter and, in some ways, stranger. It is a hole. Here is what that actually means. The sun is wrapped in a magnetic field, and most of the time, that field acts like a lid, looping back down onto the surface and holding the sun's hot outer layer close. But in some spots, the field does not loop back down. It opens straight up and out, like a screen door that got left open on a windy day. Once that door is open, the solar wind, which is just a stream of tiny charged particles blowing off the sun all the time, can escape much faster than normal. Normal solar wind moves at around 300 to 400 kilometers every second. Through an open coronal hole, it can rocket out at 700 kilometers per second or more. That is almost double the everyday speed, and it is why forecasters are paying such close attention this week. Think of the sun's magnetic field like a huge net wrapped around a ball. Most of that net is tightly woven, holding everything in place. A coronal hole is a spot where the weave came apart, leaving a gap the solar wind can pour through. These gaps are not rare or mysterious. They show up on the sun all the time, and this is not even the first time this exact hole has swept past us. Coronal holes rotate around with the sun roughly every 27 days, about once a month, which means the same gap can point at Earth again and again on a repeating schedule, almost like a lighthouse beam sweeping past the same spot on the coast over and over. This particular hole is big, and it stretches across the middle of the sun in a way that lines it up almost perfectly with Earth. Forecasters at the UK's National Weather Service, which also tracks space weather, put out a forecast saying wind speeds should hit around 450 kilometers per second on July 21st, then climb towards 700 kilometers per second by July 22nd. NOAA's official watch, issued a few days ago, calls for a G1 storm, which sits at the low end of the storm scale. That scale runs from G1, the mildest level, all the way up to G5, the most extreme level ever recorded. Think of it a bit like the scale used for hurricanes. A G1 storm is like a light tropical storm. Noticeable if you know to look for it, but nothing that changes daily life for most people. A G5 storm is the space weather version of a Category 5 hurricane, the kind that can knock out power grids and satellites across huge stretches of the planet. Tonight's storm sits right at the gentle end of that scale, which is exactly why the biggest risk right now is missing the aurora, not dealing with anything dangerous. Some computer models are hinting it could push a notch higher into G2 territory, but that upgrade has not actually been confirmed by NOAA yet. It is a possibility being watched, not a lock. So why should you care about a low-level storm at all? Because even a small geomagnetic storm can push the northern lights much farther from the poles than they normally sit. Under a G1 storm, the aurora can become visible from the very northern edge of the United States. Places like the tip of Washington State, northern Montana, and Michigan's Upper Peninsula, along with northern Scotland. If the storm does manage to reach G2 strength, some forecasts suggest the glow could stretch as far as Seattle, Edinburgh, and even Oslo. But before you run outside expecting a neon green sky, there are two things working against you this week, and honestly, they matter more than the storm strength itself. The first is the season. This is the middle of summer in the northern hemisphere, which means the nights are short and never get fully dark at higher latitudes. Aurora needs real darkness to show up to the naked eye, and this week just does not have much of it. The second problem is the moon. There's a first quarter moon out right now, and while that is not full, it is bright enough to wash out a faint aurora the same way a streetlight washes out a dim star. So, if you look up tonight and see nothing, do not assume the forecast was wrong. It just means the deck is stacked against you this particular week, even if the geomagnetic numbers behave exactly as predicted. While we are on the subject, here is a quick answer to a question a lot of people never think to ask. Why is the aurora green? When charged particles from the sun slam into Earth's magnetic field, they get funneled down toward the north and south poles, where where they crash into oxygen and nitrogen floating high up in our atmosphere. That collision makes those atoms glow, the exact same way a gas in a neon sign glows when electricity runs through it. Oxygen tends to glow green and sometimes red, which is why most aurora photos look the way they do. Nitrogen glows blue and purple, and you usually only see those colors during a stronger storm, since it takes more energy to light up nitrogen than it does oxygen. So a green sky means a mellow storm, and blue or purple mixed in usually means things got a bit more intense. There's also a detail here that most coverage of this storm leaves out, and it explains why forecasters can only ever give you a short warning before one of these things actually lands. The only spacecraft that can measure the true strength of incoming solar wind sits at a location called L1, about 1.5 million kilometers from Earth, roughly 4 times farther away than the Moon. Right now, that job belongs to a satellite called Solar One, which took over the role earlier this year. Even sitting that far out, Solar One only buys us somewhere between 15 minutes and an hour of warning before the wind actually slams into Earth's magnetic field. Everything before that point is an educated estimate. Everything after that point is happening in real time, with almost no room to react. Solar One is actually a fairly new addition to this whole system. For years, the spacecraft doing this exact job was an older satellite called DS-CoV-R, which had been sitting out at L1 quietly doing this work for close to a decade before it was finally retired earlier this year. Think of it like swapping out an aging weather radar for a newer model. The job stays the same, watch the incoming storm and radio back the details as fast as possible, but the equipment doing the watching keeps getting replaced as it wears out. That constant upgrading is a small reminder that space weather forecasting is still a relatively young science, built on a small handful of satellites, doing an enormous job from a very lonely spot in space. Coronal hole storms like this one are also not some rare, once-in-a-lifetime event. This exact type of storm has shown up before, sometimes even stronger than what is forecast for tonight. Earlier in the same solar cycle, a coronal hole-driven storm reached G2 strength and pushed the aurora down into states like Idaho, North Dakota, and Wisconsin, along with Scandinavia and northern parts of the UK, almost the identical list of places we are talking about tonight. The pattern repeats because coronal holes themselves are a normal recurring feature of an active sun, not some unique surprise cooked up just for this particular week. Now, a storm driven by a coronal hole tends to behave differently than the kind you might have seen make headlines before. It does not arrive as one dramatic punch. It arrives more like a garden hose left running on high. Steady push instead of a single blast. That actually makes it a bit more predictable days in advance, since coronal holes rotate around with the sun roughly every 27 days, which means the same hole can sweep past Earth again and again on a schedule forecasters can track. That predictability is exactly why NOAA and the UK Met Office both flagged this event days before it arrived, instead of scrambling once it showed up. Here is the honest reason I want you subscribed for the rest of this channel, and it has nothing to do with growing a number on a screen. Space weather forecasts change fast, sometimes within hours, and most channels either ignore this stuff completely or just show you a pretty photo of green lights with zero explanation of what actually caused it. I pull directly from NOAA, the UK Met Office, and NASA's own solar imaging, and I will keep updating you the moment any of this shifts, especially the part we are about to get into, which involves a sunspot that did something nobody expected. So if that sounds useful to you, hit subscribe now, because the next section explains why this hole is really just one of 3 completely different ways the sun can come after us, and the other 2 are a lot less predictable. One more tip before we move on, since a lot of people miss the aurora even when it is technically there. Your phone camera can often catch a faint aurora glow that your own eyes cannot pick up. Phone camera sensors are more sensitive to light than the human eye, especially in low light settings, so if you step outside tonight and the sky just looks like plain darkness, try holding your phone steady, maybe leaning it against a car or a fence post and taking a few second exposure photo facing north. Sometimes a faint green smudge will show up in the photo that was completely invisible standing there looking at it with your bare eyes. Section 2. 3 ways. The sun can hurt you. To understand why forecasters are watching so closely this week, you need to know something most people never learn in school. The sun does not threaten Earth in just one way. It has 3 separate weapons, and they behave nothing alike. A simple way to keep these 3 straight is to compare them to ordinary weather. A flare is like a flash of lightning, sudden and over in an instant. A coronal mass ejection is like a hurricane, a huge, heavy system that takes time to arrive but hits hard when it does. A coronal hole stream is like a strong, steady wind that blows for days without ever really gusting or calming down. Keep that comparison in your head, because it makes the rest of this a lot easier to follow. The first is a solar flare. Think of a flare as a sudden flashbulb going off on the sun's surface, a burst of radiation that blasts outward in every direction at the speed of light. That means a flare reaches Earth in about 8 minutes. the same amount of time it takes any sunlight to cross the 150 million kilometers between us and the sun. Flares get sorted into letter grades, kind of like a report card. C-class flares are common and barely register here on Earth. M-class flares are stronger, strong enough to cause a brief radio hiccup on the side of the planet facing the sun at the moment it hits. X-class flares are the strongest grade that exists, powerful enough to knock out radio communication across entire regions the instant they arrive. Because a flare travels at the speed of light, there is no early warning for one. It either happens or it does not, and we find out at the same moment the light does. There is also a real, well-documented example of the third threat causing actual damage, not just theoretical risk. Back in 2022, the company launched a batch of brand new small satellites right as a geomagnetic storm hit Earth. The storm heated up the upper atmosphere and made it puff outward slightly, which increased drag on the satellites while they were still flying low, before they had climbed to their final orbit. That extra drag pulled almost all of them back down into the atmosphere, where they burned up within days, a multi-million-dollar loss caused entirely by a storm that most people on the ground never even noticed. It is a perfect example of how something as invisible as extra drag on the edge of space can quietly wipe out expensive hardware without a single flash or explosion involved. To make that less abstract, think about an airline flying a route over the North Pole. Pilots on those routes use high-frequency radio to stay in touch with the ground, since regular cell towers do not exist out over the ice. A strong enough flare can wipe that radio signal out for a stretch of minutes to hours on the side of Earth, facing the sun, which is exactly why airlines sometimes reroute polar flights away from the pole during a strong solar event, even though nothing is actually falling out of the sky. It also helps to know why the sun does any of this in the first place. The sun runs on a cycle that repeats roughly every 11 years, swinging between a quiet phase with almost no sunspots and an active phase packed with them. More sunspots means more flares, more coronal mass ejections, and more chances for a week like this one. Right now, we are sitting inside the active phase of that cycle, which is a big part of why the sun has been so busy lately. The same active stretch already produced one of the strongest geomagnetic storms in more than 20 years, a storm that reached the very top of the storm scale and sent aurora spilling across North America, Europe, and even parts of Australia, places that almost never get to see the northern lights at all. That event is a good reminder that the sun still has room to surprise us even further than anything we're looking at this week. The second weapon is a coronal mass ejection, and this one is a completely different beast. Instead of a flash of light, picture a cloud of magnetized plasma, sometimes weighing billions of tons, getting hurled off the sun's surface like a cannonball made of fire. Unlike a flare, this cloud has actual mass, so it cannot travel at light speed. A fast one can still move at well over 1,000 kilometers per second, which sounds abstract until you convert it. That is over 3 million miles an hour, fast enough to cross the entire United States in about 3 seconds. Even at that speed, the distance to Earth is so enormous that it usually takes somewhere between 1 and 3 days to cross the gap. That slower travel time is actually a gift to forecasters, because once a coronal mass ejection is seen leaving the sun, there's a real window to track it, model its path, and warn people before it arrives. The catch is that the single most important detail, whether the magnetic field buried inside that cloud is oriented in a way that connects strongly with Earth's own field, cannot be measured until the cloud is almost on top of us. That is the same 15 to 60-minute warning window we just talked about with Solar 1. The third weapon is the one driving tonight's alert, the high-speed stream escaping through a coronal hole, which we already covered in the last section. Where a flare is a flash and a coronal mass ejection is a cannonball, a coronal hole stream is more like a fire hose that gets left on for days at a time. It tends to be steadier and gentler than a direct hit from a coronal mass ejection, but because coronal holes rotate back around with the sun roughly every 27 days, they give forecasters a rare gift, the ability to see the same feature coming back around a full month in advance. Here's the part that actually makes this particular week worth paying attention to. Most weeks, Earth is only dealing with one of these 3 threats at a time, if that. This week, all 3 mechanisms are active on the sun at once, even though the coronal hole stream is the one arriving first and driving tonight's headlines. There are sunspot regions on the disk right now capable of throwing flares. There have been coronal mass ejections earlier this month that already reached us. And now a coronal hole stream is layering a third kind of disturbance on top of everything else. None of these 3 things cancel each other out or make each other less dangerous. If anything, having all 3 active during the same stretch of days is exactly why space weather physicists keep describing this as a critical week, rather than just another ordinary Tuesday on the sun. It would be a bit like a town dealing with a heat wave, a windstorm, and a flash flood warning all in the same week. Any single one of those on its own might be manageable. All 3 stacked together is what actually makes emergency planners nervous, not because any one threat suddenly got worse, but because there is less room to recover between hits. To really understand how unusual that is, you have to rewind about 3 weeks back to the very last time the sun did something this aggressive. Because what happened at the end of June set up almost everything we are dealing with right now, and it is a genuinely wild story on its own. Section 3. The month. The sun went crazy. On June 30th, a sunspot region, cataloged as AR4479, let loose an X1.1 class solar flare, the strongest category that exists. That flare hit hard enough to trigger a strong radio blackout over a stretch of the Pacific Ocean east of Hawaii, the kind of disruption that would have made high-frequency radio nearly useless for ships and aircraft passing through that patch of sky at that exact moment. That alone would have been a notable event in an ordinary month. But this was not an ordinary month, and the sun was not done. Over the next 24 hours, that same region fired off 10 additional M-class flares, one right after another, like a machine that could not stop reloading. To put that pace in perspective, during a normal, moderately active week, the sun might produce 1 or 2 M-class flares total. This single sunspot produced 10 of them in a single day. Space weather physicist Dr. Tamitha Skov, who tracks the sun for a living, looked at the pace of eruptions and started calling the sun a machine gun. It is hard to argue with that description. 10 strong flares in a single day from one sunspot is the kind of pace that even veteran forecasters do not see very often. Several of those eruptions also launched coronal mass ejections, those billion-ton clouds of plasma we just talked about. And because they were fired off so close together in time, some of them actually caught up with each other while crossing space. A bit like 2 cars leaving the same starting line seconds apart and one gradually catching the other on the highway. Instead of arriving as separate, smaller pushes, they merged into one bigger, stronger disturbance by the time they reached Earth. NOAA saw this coming and issued a watch for a moderate G2-level geomagnetic storm on July 3rd and July 4th. Then, in a twist that is honestly a little humbling for anyone who thinks space weather forecasting is an exact science, the storm arrived almost exactly on schedule and turned out to be stronger than anyone predicted. Instead of topping out at G2, it escalated all the way to a strong G3-level storm right on the night of July 4th, and produced aurora visible across roughly 30 separate states, an area far larger than a G2 watch would normally suggest. People who had never once seen the northern lights in their entire life, in states nowhere near the Canadian border, stepped outside on Independence Day and caught a glimpse of green and red light dancing on their own horizon, all thanks to a storm that started as a modest G2 forecast just days earlier. That gap between the forecast and the actual result is worth sitting with for a second, because it tells you something true about how this whole field works. Forecasters can measure a cloud's speed fairly well the moment it leaves the sun. What they cannot measure ahead of time is the orientation of the magnetic field hidden inside that cloud, which is the single biggest factor in how strong the resulting storm actually becomes. That detail only reveals itself once the cloud reaches the Solar 1 satellite at L1, with that same short 15 to 60-minute warning window standing between us and impact. The July 4th storm is proof that even a well-studied event can still surprise the people whose entire job is predicting it. For about 2 weeks after that Independence Day surprise, the sun actually calmed down. Forecasters describe conditions through the middle of July as quiet, with weak interplanetary magnetic fields and Earth's own magnetic activity sitting near the lowest levels on the standard scale, day after day. If you were only checking the news casually, you might have assumed the excitement was over, the same way a calm sea can make you forget a storm ever passed through at all. But quiet on the sun rarely lasts long during a period like this one. And on July 17th, something new showed up on the edge of the visible disk. A small, unremarkable-looking sunspot appeared near the southeastern limb, the kind of thing that easily could have gone unnoticed. NASA's Solar Dynamics Observatory caught it on camera before it even had an official name. NASA's imaging satellite watched the little dark patch grow bigger by the hour, the kind of gradual reveal you would see in a slow zoom shot in a documentary, except this one was happening in real time on a live feed anyone could pull up online. Within 2 days, before this new region had even fully rotated into view, it was already outproducing every other flare source on the sun for 2 straight days running. That is an unusually fast rise for a region that had barely finished forming. Naturally, once forecasters saw that kind of early performance, they started paying very close attention, expecting this new arrival to become the dominant story of the week. At the same time, an older, more established region nearby had developed a genuinely tangled magnetic structure, the kind solar physicists consider mechanically primed to pop off a significant flare without much warning. So, going into this week, the setup looked simple on paper. One brand new hotshot region on the rise, and one older, more dangerous-looking region sitting right beside it. Here is where it gets interesting, because that is not exactly how things played out. Section 4. The region. Everyone got wrong. This is the part of the story most coverage of this week completely misses. And it is honestly the most interesting twist in the whole thing. Remember that promising new region we just talked about? The one that looked like the sun's next big flare machine before it had even fully rotated into view? Once it actually cleared the edge of the sun and forecasters got a full, clear look at it, the picture changed completely. Before we go further, it helps to know how forecasters actually grade how dangerous a sunspot is, because this whole story only makes sense once you understand the ranking. The simplest sunspots have one single calm magnetic zone, like one bar magnet just sitting there. Forecasters call that the mild type, and it almost never produces anything strong. As a region grows, it can develop two opposite magnetic zones sitting near each other, a bit like the north and south ends of two magnets placed close together. That is a step up in danger. The most dangerous setup happens when several opposite zones get squeezed together so tightly that they are almost touching, like a bundle of rubber bands, twisted and stretched right up to their breaking point. That is the configuration forecasters watch most closely, because it is the one most likely to snap and release a big flare. With that in mind, here's what actually happened. Instead of turning into a monster, the once promising region settled down. Its magnetic structure came in as the simplest possible type, the single calm magnet we just described, with very limited flare potential, and the sunspot itself looked smaller than early images had suggested. Some of that early hype turned out to be a bit of an optical illusion too, since features sitting near the edge of the sun's disk often look more dramatic than they really are, simply because of the angle we are viewing them from. The lesson here is a good one to remember any time you see a scary sunspot headline. A region that looks explosive while it is still hidden behind the horizon does not always live up to that reputation once it comes into full view. Now remember that other region, the older one with the tangled magnetic structure that forecasters flagged as the one most likely to erupt? That story took a turn too, just in the opposite direction. Instead of building toward an eruption, it actually lost its complexity. The tangled part of its magnetic field unwound, and it slid down into a simpler, weaker configuration. It stopped producing flares almost entirely. The region forecasters were most worried about a few days ago is, right now, one of the quietest spots on the entire sun. So, if the region everyone expected to be dangerous calmed down, and the region everyone expected to be a monster turned out mild, does that mean this week is actually boring after all? Not even close, because while everyone was watching those two regions, a completely different one snuck up almost out of nowhere. This new region emerged from what looked like a blank stretch of the sun's surface just a day or two ago, and it grew fast. It quickly developed the most tangled, complex magnetic structure a sunspot can have, the highest complexity rating on the entire scale forecasters use. To put its size in perspective, this single sunspot region is estimated to be wider than 7 Earths lined up side by side. Within days, it developed that rubber band-style structure we just talked about. Opposite magnetic zones packed together so tightly that forecasters gave it the highest complexity rating on their entire scale. In just one day, it fired off 3 separate M-class flares. A real burst of activity for a region that barely existed the week before, going from an empty patch of sun to the most watched spot on the entire disk in less time than it takes most sunspots to even get properly named. Current odds from solar forecasters put this region at around a 30% chance of producing another M-class flare the next day, and roughly a 5% chance of something even stronger, an X-class flare. Think of those numbers the same way you would think about a 30% chance of rain in a normal weather forecast. It is not a sure thing, but it is high enough that you would probably grab an umbrella on your way out the door. Compare that to the 2 regions everyone was originally watching, which have both fallen to odds so low they barely register anymore. In other words, the real story of this week is not the region that got the headlines a few days ago. It is the one that showed up quietly and became the most dangerous spot on the sun almost overnight. Solar forecasters who track the sun daily describe this shift almost in real time, watching a quiet patch of nothing turn into the most complex region on the disk within the span of a couple of sunrises. It is the kind of turnaround that keeps this job interesting even for people who have been watching the sun for decades, because it proves that no matter how good the models get, the sun still has the final say. This matters because it is a genuinely good reminder of how fast things change up there. The sun does not follow a script. A region that looks calm today can turn tangled and dangerous within 48 hours, and a region that looks like a ticking time bomb can quietly settle down just as fast. Forecasters are not being dramatic when they say they track this stuff daily. They genuinely have to, because the picture can flip that quickly. You might be wondering why forecasters cannot just look at a tangled sunspot and tell us exactly when it will erupt, the same way meteorologists can tell you almost to the hour when a hurricane will make landfall. The honest answer is that nobody fully understands the exact trigger yet. A tangled magnetic structure is a bit like a stack of loose rocks piled on a hillside. Experts can look at the pile and say it looks unstable and could slide at any moment, but pinpointing the exact second it lets go or whether it holds together for another week is still beyond what any model can promise. That uncertainty is not a flaw in the science. It is just an honest limit of trying to predict something happening 93 million miles away, using nothing but light and magnetic readings bounced back to Earth. Put all of this together and you get the actual shape of this critical week. A coronal hole stream doubling solar wind speed and driving tonight's aurora chances. A once promising region that fizzled out, an older region that calmed down instead of erupting, and a brand new region that came from nothing and within days became the single most complex, most active spot on the entire sun. NASA and NOAA are both clear that a major X-class eruption is not expected in the next few days specifically, but that assessment can shift within hours if this new region keeps growing the way it has been. None of this happens in a vacuum either. It is all unfolding during what solar physicists call a solar maximum, the most active stretch of the sun's roughly 11-year cycle, officially declared underway back in October of 2024. A solar maximum is not one single sharp peak. It stretches across a year or more of consistently elevated activity with more sunspots, more flares, and more coronal mass ejections than the quiet years on either side of it. That is exactly why this week does not stand alone. The Machine Gun Sun event in late June, the surprise G3 storm on July 4th, and this brand new region rising out of nowhere are not four separate coincidences. They are four data points from the same turbulent window, produced by a sun that is still sitting near the most active stretch of its natural cycle. So what does all of this actually add up to? And why should any of it matter to someone who is not a scientist? That is where we need to go next, because the stakes here go a lot further than a pretty light show in the sky. Section 5. What if this one doesn't stop? Here's the honest truth about space weather. The aurora is the fun part, the part that gets the photos and the headlines, but it is really just the visible symptom of something with much bigger stakes hiding underneath it. Every one of the three threats we covered earlier, flares, coronal mass ejections, and high-speed streams, can reach out and touch technology that regular life depends on every single day, often without anyone even realizing why something suddenly stopped working. Strong flares can cause radio blackouts on the sunlit side of the planet within minutes, disrupting the high-frequency radio communication that airlines and cargo ships actually rely on to stay in contact over oceans and polar routes. Geomagnetic storms of any kind, whether they come from a coronal mass ejection or a coronal hole, can throw off GPS accuracy and timing signals. That sounds small until you realize those same timing signals help synchronize financial trading systems, cell phone networks, and power grid operations behind the scenes. Think about how many things in your own day quietly lean on GPS without you ever noticing. A rideshare app tracking your driver's location. A delivery app timing when your food will show up. A bank stamping the exact second a card payment goes through, which matters far more than it sounds like, since fraud detection systems and trading markets both depend on knowing the precise order events happened in, down to fractions of a second. None of that stops working during a minor storm like tonight's. But it is a good reminder of how many invisible threads tie back to satellites quietly orbiting overhead, and how a strong enough storm could tug on more of those threads at once than most people would ever guess. Even satellites feel it. During periods of high solar activity like the one we are in right now, the upper atmosphere actually puffs up and expands from the extra energy pumped into it, which creates more drag on satellites in low orbit and quietly shortens their working lifespan. The most serious risk of all, though also the rarest, involves the power grid itself. A strong enough geomagnetic storm can push slow, direct current like electrical currents through long, high-voltage transmission lines. Those currents can overheat and permanently damage the massive transformers that keep entire regional power grids running. These are not machines you can grab off a shelf. Each one is often custom built to order for a specific power station, a bit like a suit tailored to fit exactly one person. And the wait time to build a replacement is often measured in months, sometimes even years, because there is usually no factory sitting on a stockpile of spares. Firefighters and emergency responders are trained to spot small warning signs long before a fire actually flashes over into something uncontrollable. Space weather forecasters are essentially doing the same job, watching for warning signs on the sun long before anything actually reaches the ground. To understand what a true worst-case scenario looks like, forecasters still point back to one single event from over 160 years ago. On September 1st and 2nd, 1859, a massive solar storm hit Earth that is remembered today as the Carrington event, named after the British astronomer who documented it. The aurora during that storm was so bright that people in the northeastern United States reportedly could read newspapers just from its glow, with no other light source needed. The lights were visible as far from the poles as the tropics, in places near the equator, where nobody before or since has ever reported seeing the aurora with their own eyes. Telegraph systems across Europe and North America failed completely. In a detail that engineers still find remarkable today, some telegraph operators discovered they could disconnect their batteries entirely and keep sending messages using only the electrical current the storm itself had induced into their wires. Other equipment sparked, and in a few documented cases, actually caught fire. Try to picture that for a second. A storm on the sun, 93 million miles away, reached all the way down to a wire on a desk on Earth and pushed enough electricity through it to run a telegraph machine on its own, with the batteries completely unplugged. That is how much raw energy a storm like this can carry. Back in 1859, all of this was mostly just a spectacle, since society at the time ran on little more than telegraph wires and steam engines. A widely cited 2013 risk assessment looked at what a storm of that same strength would do if it hit the modern North American power grid today, and the numbers are genuinely sobering. The estimate ranged from roughly $600 billion to $2.6 trillion in economic damage, with somewhere between 20 million and 40 million Americans losing power for anywhere from about 16 days at the low end, all the way up to 1 or 2 years at the extreme high end, concentrated along heavily populated corridors in the eastern and midwestern United States. Other estimates that factor in disrupted telecommunications, banking, and GPS infrastructure alongside the grid itself land in a similar multi-trillion-dollar range. The reason those numbers are so much bigger than anything that happened back in 1859 has nothing to do with the sun getting stronger. The sun in a Carrington-level event would behave about the same either way. The difference is us. In 1859, losing a telegraph wire was an inconvenience. Today, losing GPS for even a few hours would ground planes, confuse shipping routes, and throw off the timing signals banks use to stamp transactions down to the second. Losing satellites would disrupt phone calls, weather forecasts, and credit card machines. Losing the grid itself, even in just a few regions, would mean hospitals running on backup generators, food spoiling in stores without refrigeration, and gas stations unable to pump fuel because the pumps run on electricity too. We built an entire modern world on top of systems that quietly assume space weather will always stay mild, and most of the time it does. This week is a reminder that it will not always stay that way. It is worth knowing that this is not just something scientists worry about for fun. Insurance companies, the same industry that calculates the odds of floods, earthquakes, and wildfires so they know what to charge for coverage, have run their own numbers on a Carrington-level storm too. When an industry built entirely around calculating risk decides a scenario is worth modeling in detail, that is usually a sign the risk is being taken seriously, well outside of just the science community. We actually already have a smaller, real-world preview of what a partial version of this looks like. In March of 1989, a much weaker geomagnetic storm collapsed the entire Hydro-Quebec power grid in about 90 seconds. Not 90 minutes, 90 seconds, roughly the time it takes to read this paragraph out loud. 6 million people lost electricity in the middle of a cold Canadian night, with traffic lights going dark and heating systems shutting off, for roughly 9 hours before crews could bring the grid back online. Satellites experienced glitches during the same event, and aurora was reported as far south as Texas and Florida, thousands of miles from where anyone expects to see the northern lights. And that entire event came from a storm weaker than the one Earth barely dodged in 2012. We also came closer to a full-scale repeat of the Carrington event than most people realize, and much more recently than 1859. In July of 2012, a coronal mass ejection of genuinely Carrington-class strength crossed directly through the exact orbital position Earth occupies in space and missed us entirely only because Earth itself had rotated to a different point in its orbit about 1 week earlier. If that eruption had happened just a week later, we would likely be telling a very different story right now. Researchers estimate the odds of another Carrington-class storm actually striking Earth in any given decade at somewhere around 10 to 12%. That is low enough that it should not keep you up at night, but high enough that multiple national space agencies treat it as a real, ongoing planning risk rather than a dusty old history lesson. To put that percentage in perspective, it is roughly the same ballpark as the odds of flipping a coin and getting heads 3 times in a row. Not something you would bet your whole life on, but also not something you would ever call impossible. That is exactly why power companies, satellite operators, and airlines do not treat space weather as a fringe topic anymore. Grid operators in several countries now have specific plans for powering down or adjusting transformers ahead of a severe storm warning, the same way a coastal city might board up windows ahead of a hurricane. None of that requires you personally to do anything differently today. It just means the systems working quietly in the background, the ones keeping your lights on and your phone connected, are being watched a lot more closely than most people ever realize. That is really the whole point of a week like this one. Not fear, just awareness. The sun has been doing this for billions of years, long before power grids or satellites ever existed, and it will keep doing it long after. The only thing that has changed is how much of our daily life now quietly depends on staying on the sun's good side. So what does all of this actually mean for you, tonight and in the days ahead? If you live anywhere near the northern edge of the continental United States, in northern Europe, or at similar latitudes in the southern hemisphere, it is worth stepping outside after dark tonight or tomorrow night, getting away from city lights and looking north. There is a genuine, if modest, chance of catching some aurora through July 22nd. If you look up and see nothing, remember what we covered earlier. Short summer nights and this week's moon are working against you no matter what the geomagnetic numbers actually do. Beyond the aurora, if your work involves aviation, GPS-guided equipment, or anything relying on precise satellite timing, it is worth knowing that NOAA's Space Weather Prediction Center publishes free public forecasts, the same way your local weather service does for ordinary storms. Checking it during a stretch like this one costs nothing and takes about a minute. The bigger lesson from this whole week is not that a Carrington-level catastrophe is about to happen. The specific mix of speed, timing, and direct alignment required for that kind of event is genuinely rare. The real lesson is that our dependence on GPS, satellites, and interconnected power grids has grown enormously since the last truly severe storm hit us back in 1859, while the hardening of our infrastructure against that exact risk has grown a lot more slowly in comparison. That gap is exactly why space weather agencies around the world treat weeks like this one as worth tracking in real time, rather than something to shrug off until it actually becomes a problem. Somewhere tonight, a farmer is relying on GPS-guided equipment to bring in a harvest. An airline is rerouting a polar flight path to avoid a possible radio blackout. And a grid operator somewhere along a busy stretch of the eastern power grid is watching a control room screen a little more closely than usual. All of it traces back to the same sun that might also give you nothing more than a faint green glow on your northern horizon tonight, if you are willing to step outside and actually look. We are going to keep tracking this exactly the way we did today. Straight from NOAA's Space Weather Prediction Center, the UK Met Office, and NASA's own solar imaging. Not recycled aurora photos with zero explanation behind them. If you want to know the moment that new, rapidly growing region does something bigger, hit subscribe and turn on notifications, because based on how fast it went from nothing to the sun's most active spot in just a couple of days, it probably will not stay quiet for long. If you want to go deeper on any of this, I have another video breaking down exactly what happened during the July 4th storm, and another one walking through the Carrington event in full detail. So check those out right after this one. Drop a comment and let me know if you caught anything in the sky tonight, and where you were watching from. See you in the next one.